Okay, hello everyone. My name's Ian Smith. I'm a technical content manager here at MIPI Alliance. I'd like to welcome you to this session, Enabling Long-Reach MIPI CSI-2 Connectivity in Automotive with MIPI IP. I'm going to shortly hand you over to Licinio Souza, who's Senior Product Marketing Manager at Synopsys, and Ido Cohen, who's a Director for Strategic Innovation at Valens, to give their presentations. You can download these presentations using the link provided in the chat window. Fortunately, after this presentation, we'll have a short period of time for Q&A. We'll try and do that live. Time is quite tight, so if you can submit your questions during the presentation via the purple chat window, that would be very much appreciated. Okay, that's my very quick introduction. Without further ado, I'd like to hand over to Licinio to start his presentation. Over to you, Licinio.
So looking at what's going on in automotive, the key trends, I want to start by talking about the transition from a more distributed ECU kind of architecture to a more centralized domain architecture. So if you look, for example, at current implementations today, especially in high-end cars, you can see up to 100 ECUs running different applications. These domain controllers in the new architecture, they are connected with a wired harness to the gateway that takes care of getting the data in and out of the vehicle. And in these new domains, we see a number of new applications in ADAS, infotainment, connectivity. Things like emergency braking, adaptive cruise control, and lane keeping. And these applications, they have their own requirements in terms of hardware and software. They also are driven by a growing number of sensors and different types of sensors, different sensing technologies like imaging, LiDAR, radar, and some applications even infrared. The system, these applications, they need to address the safety and reliability expectations to prevent failures. So they need to address the functional safety requirements and the reliability requirements as well. So we're talking about complex systems that process massive amounts of data, and given the complexity, we definitely see them being moving to advanced FinFET technologies. So zooming in into these safety critical applications using MIPI in automotive. We see these applications in ADAS, in IVI, things like the rear view applications, e-mirror, park assist, and surround view. So what I have here on the left side is a very simple representation on how to implement these applications. You have the SoC, the ECU, the domain controller that has the processing capabilities, the memory interfaces, and also has the necessary interfaces to enable these applications. That includes MIPI CSI input to bring in the different sensing technologies in, the different data from the different sensing technologies into the SoC, and then also the DSI transmitter to drive the different displays in the car. So as you can see here, obviously these chips are not placed right next to the sensors, right? So there's a need to use a long reach technology to bring the data into the SoC. And that's actually what Ido will talk soon in terms of when talking about his use case from Valens. On the display side, again, the same thing happens. DSI displays are being used in the car for some displays inside the cluster, or for the e-mirror, or for the rear view. So again, there's also a need for a long reach connectivity in order to connect the SoC to these devices, to these peripherals. On the right side, I'm kind of stating the obvious. When you're designing for automotive, it's different from when you're designing for consumer applications. There are fundamental differences because of the operating conditions, the temperatures, the lifetime expectation, the failure rate that needs to be pretty much zero. And so when you're designing for automotive, you really need to address the functional safety, reliability, and the quality requirements in automotive. So we're going to talk a little bit about these in the next few slides. Starting with functional safety, what I have here is kind of this visual shows you the development flow for functional safety, ISO 26262 functional safety. And the key point here is that when you're designing for automotive, there is a number of activities, operating steps, work products that need to be added to the development flow. So if you look at a typical V-shaped model, On the left side, we have the architecture, the implementation, and on the right side, we have the verification and the validation. So if you look at what's going on the left side, around the time of the architecture and the specification, when you're designing for automotive, you need to start looking at, you need to put together the safety plan, you need to define the safety goals, and then you need to implement these safety features that will help you address these safety goals. And when we move to the verification, one important requirement of functional safety is that you need to perform fault injection. You need to go through this exercise and analyze the design and make that safety assessment. The output is the FMEDA report that is an assessment of safety to make sure that the design is able to meet the target safety levels, typically described as ASIL B, C, or D. Then everything rolls into the safety manual where you have information about the safety level that you can target, but you also have details about the safety mechanisms, the safety features that were implemented, how to use them, how they behave. And these safety mechanisms, they can be internal to the SoC or to the IP, or they can also be external. And these would be assumptions made by the safety team that infrastructure will be in place to make sure that this block, this SoC can achieve the target safety levels. So looking at an example, here I'm bringing in an example of a CSI-2 interface that is meeting the safety requirement, the safety level for ASIL B. And so this is an example, and if we look at what industry providers are doing, kind of as the best-in-class example, there is a need to add additional capabilities because the protocol itself doesn't support those natively. CSI-2 today is still evolving, right? There's a new version of the spec that is being put together that will definitely address some of the requirements in automotive. But if you look at current implementations, what some of the industry providers are doing, they're basically adding additional capabilities to make sure that the building block, the CSI-2 interface, can handle the target safety levels. So here's an example, taking the block. What the type of features that you need to add are things like the protection of the user interface, adding parity protection to the user interface, the interface between the block, the interface, and the SoC, adding parity protection to the internal data paths, adding, if you look at these buffers and FIFOs that you need to implement the protocol, you need to make sure that you have ECC protection on those memories, on those buffers and FIFOs. The register space protection is also extremely important. The last thing you want is to have one of the bits flipping and changing the operation of the interface. And so you definitely need to look into having robustness to the register space. And then looking at critical circuits inside the design, clock domain crossings, critical state machines. You want to make sure that you add redundancy to make sure that you will not run into an issue there. So all these features put together will enable this building block to achieve the target safety levels, in this case ASIL B, or even beyond. And each feature, they have their own behavior, they have their own mechanisms, their own reaction time, their own flags, and they need to be managed at the system level. And that's actually what I bring in the next slide, which is we take care of the building block, the CSI-2 interface, and now we're bringing it in at the SoC level. And the functional safety strategy that was implemented at the IP level and at the block level, it needs to link with the system level view of functional safety. And that's kind of what I'm showing you here as an example. This is an industry technique, very common, which is to have a dedicated entity, a safety manager processor with its own stack that ultimately is offloading everything related to safety from the other processors that are actually running the application. So this entity will basically manage and monitor everything related to functional safety, will manage the system failures, the real-time faults, and also takes care of things like safe boot, vision mode testing, and even logic BIST. It's very common in automotive. Upon startup, you want to run all these logic-based testing to make sure that all the building blocks are working as expected. So moving to the next slide here. So sorry about that. So we talked about functional safety, and I want to switch gears to reliability, the other important requirement that I mentioned at the beginning. Now, these systems, they need to handle stringent operating conditions. The environment, the temperature, the noise, the vibration, the long-term operation, these devices, these systems need to work properly for 15 years at least. And the target field rate is definitely very low, targeting 0% effectively. So these designs, they need to be very reliable. And one thing that we kind of heard, and probably everybody knows, is the ACQ 100 standard that defines tests and procedures to qualify these electronic parts for automotive. And it defines also the tests that are needed, for example, HTOL, high temperature operating lifetime. So these are stress tests. The point here that I want to make is that when it comes to qualifying for automotive, in order to make sure that you're qualified for automotive, that you pass these tests, you want to make sure that you designed for reliability. So you need to address a number of items at the design stage. And one important input here is to really look at the target application. What kind of temperature profiles will it be exposed? And that depends on the application, whether it's something that will be inside the vehicle, inside the cabin, or outside the cabin, under the hood. Different temperatures that will be exposed. And the temperature will effectively guide the design rules and the tech files that you bring in at the design phase. Just to elaborate on the dependency between temperature and the technology, at higher temperatures, you have higher current densities, and that will affect the electromigration specs of the technology. So the design rules need to accommodate as well. So you take care of that at the design stage. Then you, when you have your GDS and you go to silicon, then you will be able to guarantee you will have more confidence that you'll be able to qualify for automotive. So the point here is designing for reliability so that you can qualify for automotive. That's here's an example of what we do with our own C-PHY IP, where we go through the exercise of putting together some test chips, and we go through the ACQ 100 testing and reproduce that reliability report. So we talked about reliability. Slide transition is taking a little bit longer. So we talked about functional safety, how the B model, the work products that need to be added to the development flow. We talked about reliability, the importance of understanding the temperature profile, the mission profile, the importance of bringing in the right design rules and tech files into the design process so that you can then implement your chip and be able to qualify for automotive. We didn't talk about quality, but well, quality like in every industry is very important. In automotive is of paramount importance. You need to really you need a very robust quality management system to support the entire development flow. And more important than that, actually, or also very important, is the fact that in automotive, you need to provide evidence of that process. So having traceability throughout the process is very important. So again, developing under a rigorous quality management system is very important. So my point here is, on the left side, kind of summarizing that point. On the right side, my point here is that if you're designing your SoC for automotive, obviously you need to make decisions about your architecture, which building blocks are needed, and in terms of the interfaces, yes, you really need to take care of the protocol, which versions, what type of protocol you want to support. And then obviously, if you want to source building blocks to add to your architecture, you need to make sure that the protocol is covered. But beyond the protocol, you also need to make sure that the deliverable, the IP, also helps you, supports all the activities related to safety, reliability, and quality. And so consider that as an automotive grade package that takes care of the protocol and all the automotive requirements that are safety, reliability, and quality. This is what ultimately will help you accelerate the development and make sure that your SoC will be qualified for automotive. And with that, I want to switch to, want to hand it over to Ido, bringing us a really interesting use case from Valens using Synopsys DesignWare, MIPI CSI, and D-PHY IP. Ido, please go ahead.
Thank you. So, as mentioned, my name is Ido. I'm Director of Strategic Innovation in Valens, and also a co-chair of the A-PHY working group. In the next 2 slides, I will try to give some more details about how we worked with Synopsys in order to expedite our work, as Valens was aiming to be and succeeded to be the first company to introduce A-PHY compliant products. And it was important for us to make sure that this is something that will be a mature and working properly in as fast as possible. And for that, we looked for a partner that can provide a mature and established IPs which can be utilized in the automotive, and let Valens focus on the core technology to meet its goals. So we were focusing on the new technology of the A-PHY, and we worked together with Synopsys to utilize their IPs for C-PHY, D-PHY, and CSI. So this was very, very helpful during the development process, having an IP that is already including safety and AEC Q100 qualification. So Valens was able to, with this support, Valens was able to provide the first samples coming from the fab in the last few weeks, and leading customers will receive the new and first A-PHY compliant products by Q4 this year, which will include CSI serializer, CSI-2 serializer utilizing the MIPI A-PHY up to 8 gigabit per second, which is Gear 3, and Synopsys CSI controller and D-PHY on this product. And of course, on the other side, there is the D-serializer, which has 2 flavors. One is a dual receiver, and one is a quad receiver A-PHY, which each port can support up to 8 gigabit per second. And Valens is already working on the next generation of A-PHY, and we continue our collaboration with Synopsys in order to provide good quality and in a timely manner to the market based on A-PHY compliant solutions. In this specific use case, so we actually looked at a solution that can support 4 cameras utilizing CSI-2 converted to 8 gigabit per second A-PHY, all getting into one single quad receiver on the other side, and being able to also receive one local CSI-2 and exit or transmit outside to 2 CSI outputs, either to one SoC or 2 SoCs, depending on a specific use case coming from the customer. So in these products, you can see the A-PHY capability and the CSI RX controller with an ASIL B and C-PHY D-PHY RX grade 2 in the serializer side on the 7031, and you can see on the receiver deserializer side, you can see the CSI TX controller, which supports ASIL B, and the C-PHY D-PHY TX grade 2. So all in all, we have end-to-end solution that has the new capabilities of A-PHY with all the spec compliant and very low packet error rate, very high noise immunity, 8 gigabit per second, and utilizing the established CSI IP coming from Synopsys. So thank you, and we can go back to you, Luciano.
Absolutely. Thank you, sir. And just to summarize the talk here, thank you very much, Ido, for the detailed overview of the use case. Very exciting application and leveraging Synopsys IP. So the summary for this talk here, we talked about the trends in automotive that are driving new SoC architectures and advanced in being used in using advanced FinFET processes. We talked about MIPI IP in automotive, these safety critical applications that require ASIL B, ASIL D ready automotive-grade IP for that, and how this can help designers to save time and accelerate the development. That package, we also talked about the importance of designing following the high standards of quality in automotive, and the fact that IP that it's already tested for ACQ 100 will definitely accelerate the SoC qualification. And then finally, we heard from Ido, a really cool example from Valens on how they use Synopsys automotive-grade MIPI IP for camera to accelerate, and how it accelerated the Valens automotive SoC design. With that, that's the summary of the talk. Well, another note that I have here, just a final slide, is just an overview of the Synopsys portfolio for automotive. So Valens did use the CSI RX and the CD-PHY, and also the CSI TX with the same CD-PHY for the transmitter. Those are the two components that we have in the portfolio. We also have another solution for display, the DSI transmitter, that also couples with D-PHY or a CD-PHY combo to drive different displays in the vehicle, as I mentioned throughout the presentation. So that's kind of the summary of the portfolio available in 22, 16, and 7 nanometer. I also leave you a few resources here if you want to double click on a few things that we talked today. And with that, I want to thank you, and I hope you enjoyed the rest of the event. Thank you very much.
Thank you.
Okay, so that's our presentation. If Ido, Lucinho, please turn on your webcams. We've got a couple of questions, obviously, here in the chat already, which is great to see. If you do have any additional questions, please submit them through the purple chat area. I see a couple of questions here already from Jeff Nightingale, both regarding the 8 gigabit per second A-PHY link. First one, what is the max reach of the 8 gigabit A-PHY link, Ido?
Okay, so this 8 gigabit A-PHY is compliant with the A-PHY specifications, which for a coax they have 15 meters, and for STP it's 10 meters. But the distance here is an example. The main thing is the channel, and any cable that is compliant with the A-PHY channel is also supported by these components.
Yeah, thank you, Ido. So yeah, obviously, you know, if you want to check out more information on A-PHY, we've got lots of information on the MIPI website that talk about the channel properties and the properties of the specification. Another question here. Obviously, Ido, you were talking a lot about A-PHY. Lucinho, you talked in your presentation about C-PHY, D-PHY. Perhaps you could just give a little bit of sort of clarification about, you know, what makes the best sense in terms of the overall PHY solution within automotive applications. Lucinho, maybe share your thoughts on that. I think you're muted, Lucinho. Let's go to Ido first in that case.
So I I think that as usual, it's important what is the use case. So depending on your required bandwidth, simplicity, this is a user decision that needs to be made. Of course, there is a main difference between A-PHY when comparing to C-PHY and D-PHY, which is the long reach support. So I think that the main discussion would be between C-PHY and D-PHY. And as usual, this is something that is dependent on the use case and the expected performance.
Yeah, I can add something there. Maybe, Ian, you can hear me there now?
Yes.
Absolutely. So there's the long reach that Ido touched there. If we look at implementations today on the road for the camera connectivity, you'll see D-PHY being implemented, right? So that's definitely something that it's already out there. What I can add here is basically from where I'm sitting, servicing this market, I can definitely say that the new designs for the camera interface, for the camera input, they're looking to support both C-PHY and D-PHY. So a combo, what is common to see here in new designs in automotive, the ones that are already ongoing now, include both a combo implementation on the RX supporting both C-PHY and D-PHY. That gives them that future proof also because the image sensors, we know what's going on there. From an interface point of view, they're also moving more and more sensors moving from D-PHY only to C-D-PHY. So having that level of support on the SoC side makes sense. And also in advanced FinFET nodes, right, something that we touched on this presentation, these chips are definitely being targeted for really advanced FinFET nodes. So a C-PHY, D-PHY combo implementation in advanced FinFET node, it's kind of what I'm seeing from where I'm sitting.
Yeah, just to add one thing, I completely agree, and this is also the flexibility of design and future proof. This is one of the reasons that in Valens product, the 7044, the deserializer, there is a combo of C-PHY and D-PHY, exactly for that reason.
So,
okay, thanks, guys. So perhaps just time for one quick last question. Obviously, in your presentations, I think you mainly focused on camera applications, but obviously the solutions are applicable to lots of other automotive applications. Perhaps you could just give a summary of those other applications and what we might see. Lucinio first, maybe?
Definitely there is, as I mentioned in the presentation, definitely camera interface, camera input, CSI input, where you can actually bring in different sensing technologies, image sensors, LiDAR, radar. One way or the other, you can actually accommodate those devices with the same conduit, with the same CSI conduit. In terms of other applications, there's the display, right? Display in automotive, as I mentioned, there are different types of displays in the vehicle. Some of them can be addressed with different protocols, with different interfaces, but there's definitely a class of displays. There's 4 small form factor displays that can definitely leverage DSI. Things like the in-mirror applications, replacing the glass with little camera on the outside to reduce the drag, to bring more efficiency, more fuel efficiency, reduce the emissions as well. So that's also an interesting trend. The rear view display, we're bringing more data there, remove those blind spots, have more data there on that rear view display, and some small displays in the cluster as well. So those are all candidates to use DSI. And potentially, given the fact that they're also a little bit distant from the domain controller, there will be a need for a long reach technology to enable connectivity between those devices and the SoC.
Okay, thank you, Lucinio. Fortunately, we've already run out of time for today's session. Obviously, get in touch with us if you have any additional questions, and we'll respond to you offline. All I can say is thank you to Lucinio and Ido for the presentation today. Please stay tuned. Our next session is from Mixel, where we learn more about MIPI D-PHY and CSI-2 for IoT AI edge devices. Thanks a lot, everyone.
Thank you.
Thank you.